I am back again. We're doing normal distribution. Last video was long. Maybe this one will be short. It's 6.2. But this time it happens in the real world, which should be exciting for us. So I'm in this one. I just did standard normal, but now we're gonna do real applications of this. So hopefully it'll start making some sense. All right, we'll look at the chapter, and there's a ton of problems. As usual, I'll try to do as many of them as I can. So here we go. I'm gonna get to my book. I think I have it on a separate tab. I do. So here we go. You made it to 6-2. All right. Okay, so 6-2. Oh, these are just more problems. Now, why you don't have to do these? These are probably more important, but I'm never going to question it. So here's 6-2. Before the means were 0 and 1. How often is a mean 0 and a standard deviation 1? Never. So I'm going to take the same ideas that we had before, but now the mean's going to be different. Standard deviation is going to be different. So how do we get the z-score? In case you forgot, I knew it would come right back up in here. That's why I didn't go through it last time. But how do we get that z-score? Here it is. Your z-score is your x value minus the mean over the standard deviation. So this is your input or your x. We're subtracting the mean, and this is population mean right here. We're dividing this by the what? The population standard deviation. Oh, our z-score is back. All right. So 611, conversion from a non-standard distribution to a standard one. The area in any normal distribution bounded by some score x is the same as the area bounded by the standard one. Cool. So before we have this is what we have. As long as we do this little formula, we can take our beautiful probability curve, our standard one, which is zeros, and turn it into this one. So this one is our mean, and all of these are our actual standard deviations. That's all it's saying. So everything we did everything we did previously, as long as we do this little conversion, we can pretend it's standardized. That's what it's showing us. Cool. So to do it, we sketch the normal curve, we shade it. For each row branded, we use the technology. Then we can use the technology or the table. All right, I think we're just going to jump right into it. So heights of men are normally distributed with a mean of 68.6 inches, standard deviation of 2.8. What a surprise. Height. Find the percentage of men who are taller than a shower head of 72 inches above the ground. So, sorry, I want to just show you how to do. So the first thing we're going to do, first thing I would do is make my z-score. That's the first thing I'm going to do. First thing I'm doing here is making a z-score, which we know it's x minus mean over standard deviation. That's the first thing I would do. So we have the mean. So we want to know everybody who's taller than this. So this is above the critical value. Usually we go to the left on the picture or the graph, so we'd have to subtract one, or we can cheat with the StatCrunch thing. Never seen StatCrunch before, but guess what? Here we go. It's 72 minus 68.6 over what? Our standard deviation is 2.8, and this is going to give us what we need. 72 minus 68.6. So we know it's 3.4 divided by 2.8. So our z-score is what? 1.214, or whatever we want it to be. So normally it looks like this, right? And we want 1.214. Compute. However, we want everybody who's taller than this, right? So if we know 88.888 or 88.8% is smaller, we just subtract it by 1. However, this one does this move. None of the other ones does this move, and we can just get the 0.112. That's what we got, 11.2%. Ta-da! I'm assuming this is what it's going to give us. Redrew the picture. 11.2%. I love it. And that's what we got. Okay, cool. 1.21. Use the technology. 0.113. Okay. I'll survive. 11.2, 11.3%. I'm over it. So about 11% won't be able to use the shower head. Let's do another one. I knew this would be really easy once we did the last one. So, all right, so z equals x minus mean over SD. Sorry, we need the population one. So I might as well do it the right way. So Air Force pilots are between 64 and 77. Heights of women with a mean are normally at this, with a standard deviation of this. So we have to do this twice. So the first one is going to be 64, that's our first one, minus 63.7 divided by 2.9, right? This is our lower value. And our other one's going to be the tall ones. So 77 minus 63.7 divided by 2.9. And this is our upper z value. And we're just going to let the calculator kind of help us out. 64 minus 63.7.3, obviously, divided by 2.9. So we know our lower one's going to be 0.103. And our upper one is going to be what? Is 13.3 divided by 2.9 is going to be 4.586. If we wanted to draw this as a picture, right? If we want to visualize this as a picture, we know that our mean is going to be 63.7. So, and every standard deviation away is what, 2.9. So we know if we add this, this is why I round for everything. That's okay. Don't have to round. 66.6. 69.5, right? So this is, and then the third standard deviation away is 72.4. Now, for hours, right? We basically want from right here, almost the middle, to the end, right? 77 is all the way over here. So this is gonna be just about half. This should be about 50% when we're done. This should be about 50% of the scores. This is how we can visualize it. We know it's going to be about 50%. However, we have to do what? We have to figure out exactly what percentage of people that they want. So we can use the StatCrunch again. I'm going to go to the between. Our first z-score is 0.103, which was just about half. See how close it is to the line, 0.103. And our other side of this is going to be 4.586. You compute the thing. Did I say it was about 50%? Look at that. 0.459. 0.459. So this is 46%, approximately 46% meet the height requirement. Ta-da! We got it. Cool. Let's see what else we got. Finding values from known areas. Okay. As usual, when does it get tough? When you have to go backwards. Don't confuse z-scores with areas. Choose the correct right and left side of the graph. Value separating the 10% from others will be located on the right side of the graph. The bottom 10%, a z-score must be negative. When it's located to the left half, areas are always between 0 and 1. Sketch the curve. If using technology, refer to the text center. If using A2, refer to the body of it. I'm probably going to be using Excel for this. If you know Z, you must convert to the equivalent X value, 6-2, by entering the values of mean, standard deviation, and z-score. So here we go. X equals your mean plus your z-score times your standard deviation. All right, I'm assuming we need an example. When designing equipment, one common criterion is to use a design that accommodates at least 95% of the population. What is the height of a door that would allow 95% of people to walk through? Based on data in Appendix B, assume that the heights of adults are between 66.2 and 3.8. How does this result to be 80? Okay, so they want us to sketch this thing first. I'll sketch it first. We know it has a mean of 66.2 and a standard deviation of 3.8, which is fine. So the first one's 70. That's 1 SD. This is going to be 1 standard deviation away and 68% of our scores. And now 66.2. Minus 3.8 is going to be 62.4. Let's do another one. So minus 3.8. It's going to be 58.6. And 70 plus 3.8 is going to be 73.8. And so this one's going to be what? 95% of our scores. There's my sketch, okay? So we want to know it's got to accommodate what? What is the height of the door that would allow 95% of people to walk through based on the data, right? We know it's going to be between what? 58.6 and 73.8. We should already know the answer, right? So how does this result compare to the height of a door at 80? 80 is too high, right? So we just want the right side. Because obviously, if it's this tall, the shorter people can walk through it too. So our answer should be 73.8. So let's actually do the math, right? So there's your formula. We've got everything we need. We want X, which I think X is gonna be 73.8. So they say our mean is 66.2 plus our Z score is 95%, so that's 0.95. And then we just have to multiply this by what? Our standard deviation, which is 3.8. Let's see what we get. .95 plus 3.8 is 4.75, which we add to the 66.2. 70.95. So I'm off. That's what our X is, 70.95. See if I made a mistake. See, we want everything to the left of this, which is 0.95, right? We want everything here. Oh, first we have to go backwards and get with the 95th percentile because I put the percentile here instead of the Z-score. So that's my mistake. Guess what? Do we make mistakes? Of course we do. So the first I have to figure out what the Z-score is based on this 95 percentile. That's the first thing we have to do, which isn't really hard, I promise. It's not going to be tough. I don't know why it won't let me draw, but guess what? Sometimes it gets rid of your drawing capability and you just got to roll with it. All right, so the first thing I have to do is get that value. I need the 95th percentile. What is that Z-score? Could we use the table? Sure, but I'm going to use Excel. So equals normal dot inverse. We want 0.95 for 0 and 1. Why are we allowed to do this? Because we're going to go backwards anyway. I got the 1.644 here, and that's what goes here. And maybe this will give me the right answer that I think we need. All right, I got 6.2472 plus 66.2, 72.44. Let's see if this is the right answer. Let's see if this 72.447. Usually, let's do 2 decimal places. Let's see if this is the right answer, 72.45. Because guess what? We all make mistakes. 72.45. Look at us. We got it. We got it. Isn't that beautiful? Step 3. Oh, then they're doing this algebraically. We did ours algebraically once we got it, just like this, 72.45. And they want to round it to 2 decimal places. So this means the height that we want, well, 1 decimal place, X is approximately 72.5. This means just about everybody can get through that door. 95% can walk through it. And I feel like we're good. High would be what? Greater than 0.05. Low is less than 0.05. That's significantly high and low. So let's do another example before we get to the it. So here it is. Use the preceding criteria to identify significantly low birth weights, okay, based on data set 6, births in Appendix B. Assume that males have a normally distributed birth weight of 3,272.8 grams and the standard deviation of this. Okay, so we first want to figure out significantly low birth weights. All right, so I'll show you how I would do it. And guess what? If I get it wrong, I get it wrong. So here we go. So significantly low. We have our little formula. X equals mean plus Z times standard deviation. Starts with X equals, right? Mean plus Z times standard deviation. Now, we don't have the Z. The first thing we have to do is get that Z. How can we get that Z? Well, if we want something really low, right? Less than 0.05, this Z-score, we want the percentile of 0.05, or you can think about this, we want the Z-score at 0.05. So that's the first thing I'm going to do. How can we do that? You can go right to Excel. Normal dot inverse 0.05, because we want less than that, which is good. 0, 1. Let's see what we get. Negative 1.645. Negative 1.645. That's what our Z-score is, okay? We just want what that has to be. We know our mean is 3,270. Sorry. 3,272.8 grams plus a negative 1.645 times the standard deviation of 660.2. So here we go. 1.645 negative times 660.2. See how it's getting smaller, right? We want this to be smaller. Now we have to just do what with this? Add 3,272.8 for the weight. And as long as this is the cutoff, so 2,186.7 pounds. If you're anything lower than that, you have a significantly low birth weight. That's what that means. That's what we want. 2,186.8. I guess I rounded it wrong at some point, but 3,728 negative 1.2. We got everything right though. Cool. All right. We did it. Guess what? It's time for some problems. All right. I knew these would be easier. 1, 2, 5 through 8. I'm not gonna do. I'll do some. I won't do them all. But let's do some of them. Let's do number 1. Hershey Kisses, data set 38. The weights of Hershey Kisses are normally distributed with the mean of this. What values of the mean of the standard deviations? What are the values of the mean and standard deviation after converting all weights into Z-scores? And what are the original weights in grams using those Z-scores? I'm not quite sure what they want us to do. Isn't that exciting for me? All right. Do they want me to convert every single one of these to a Z-score from Appendix B? Okay, I'll do it. It's weird. Okay, so we have a mean of 4.5338. we have a standard deviation of 0.1039. And we need to find the z-scores, x minus the mean, divided by our what? Our standard deviation. So if this is what they want me to do, I'm going to go for it. Appendix B. Hershey Kisses. Number 38. Woo. Here's the Hershey Kisses. But these are just the first 5 rows. Do I just do the first 5 rows? Do I do them all? All right, so how would I do this? I'd probably just do these 5, right? But if they want them all, right? If case they want them all, I'm gonna show you how we can do this with Excel. Because, honestly, so I'm gonna go back to StatCrunch and where are data sets? We got number 38, which is candies. Maybe it's in my data sets. Nope. What if I just put 38? Maybe this is it. Weight in grams of 50 candies. I'm going with this one. Nope. I'm pretty sure I downloaded this into Excel previously when they told me to get all the data sets. So that's what I'm going to do. Downloads. Mini tab data sets. Sweet. I knew I got it at some point. Okay. Well, that's frustrating. Triola data sets. Cool. So download all the data sets. Candies come up. Oh, that was annoying. So I'm gonna just show you how you can do them all at once because honestly, I don't want to do 5 by hand. I don't want to type them in. We have the data sets, just re-download it. It's in a previous video. You go to data sets, it should come up right away. We're downloading all the data sets. And I will get to candies as soon as candies wants to open for me. How can we get the data sets? You can go to home. You know what I'm gonna do? I'm gonna put this right into the homework for you guys because obviously I don't want you to have to search for it because that would be really annoying, right? That's what I'm gonna do. Thank you for starting early on your next week of work, those who did. I'm pushing this school laptop real hard in this moment. I can try again. Here we go. And I'll put it in both of them. So this was 6.2, book assignment. Man, I'm almost at the end of these, which is nice. Now, if it would open, that'd be even better. Or I will do it when it stops, when I stop recording, I guess the computer can't handle opening these, which is real sad, but I'll put them in after, I promise. So in 6.2, you will see this this thing. All right, I'll show you how to do it though. I'm gonna sit here for a second. I'm gonna sit here, and I'm gonna show you how to do this with Excel. So your life is easy. So you don't have to do all these things by hand. So we just care about the Hershey's, right? So I'm gonna get rid of these peanut butter cups. So I just have something next to the Hershey's. Yeah, I know. I'm doing too much. All right, so here's our formula, right? So to get all the Hershey's, they want them all. Guess what? We'll give them all the Hershey Kisses. Wait, so basically, I'm gonna call the Z-score of the Hershey's. So it's Z sub H. So I guess I'll do a little H next to it. First thing I'm gonna do is equals. I'm gonna put the formula. So we know what's the mean, right? So I'll put in parentheses. The mean is what? Actually, it's the first value. So here it is, G2 plus. Sorry. The mean is, it's the Z-score. We don't have to go backwards here. So that's when you're going backwards, but here we have the X. So it's going to parentheses, your X, which is your value, minus the mean. In this case, our mean is what? 4.58338. And I'm going to divide that by hitting the one that's under the question mark, standard deviation, which we know is 0.1039. Boom. So there's our first Z-score. What can I do with these Z-scores? I can drag these down and it's going to do them all. See how it's doing them all? Isn't that beautiful? Ta-da. These are all every Z-score. Now, if you want the exact Z-scores, if you want these in order, what can we do? I can just sort this by going to home, sorting this from smallest to largest, and I will expand so they all match. Now, every single thing is perfectly in order. I have every Z-score in order. And you know what I'm going to do? Okay, now I see the data. I'm going to copy these, and I'm going to put it right here. Not letting me copy and paste. That would be annoying. Here it is. Sweet. So there is 1A. They wanted every Z-score. We gave them every Z-score, and guess what? We also put them in order. Cool. Let's go to the next one. Remember, we are on 5. Sorry, we are on 6-2. Oh, it's because it's minimized. So that's the first one. All right, let's see what else they want us to do. All right. Here we go, 6-2. Basic skills and concepts. What are the values of the mean and standard deviation after converting all the weights of Hershey Kisses into z-scores? What are the values of the mean and standard deviation? Well, the mean and standard deviation, if they're all z-scores, should be 0 and 1. If that's all they wanted, so I did all that extra work for nothing. But basically, we get the mean of this and the standard deviation of this, you'll see that it's just going to be 0 and 1. So here we go, equal average. Ta-da. Should be 0. Okay, so it's H2 to H76. I guess I didn't have them all. Well, it should be 0 and 1. I don't know why, after doing all the math, we're at like a little bit off, which is kind of a shame. And I'll do the standard deviation, but it should be 0 and 1 if they're all changed to z-scores. I guess there's something off with their data, or this formula doesn't account for rounding. Something is off with this, but let's actually. Oh, they won't let me go back to the original data. All right, so I'm getting rid of this. I'm doing it again. Whenever something is, we know it should be 0, -1. When something doesn't come out, guess what I do? I mess with it. Here we go. I ordered the column. Let's get the z-scores using exactly what they want. So equals. The z-score is going to be our x value minus the average. And they gave us the average. I didn't come up with the average. 4.5338. We're going to take that, we're going to divide this whole thing by the standard deviation, which is 0.1039. So we have our first z-score, which is this. Now, since I made this, we should get them all. Nice and in order. And now all I have to do is get what? Equals average of all of these z-scores. And this should be what? This should be 0. If it's not 0, they done messed up. That's close enough to 0 for me. Beautiful. So here's our average, which we can see is 0. If I do the standard deviation of this, I should get 1. STDEV dot. We're going to do population. It's a sample, but we're trying to say this is the population of all of them, right? This stands for population. So I think I got to go P here. Let's see what happens. Otherwise, the only thing that changes is they're not n-1. Otherwise, I'll go with the sample. See what we got. Did we get 1? Very close to 1. Let's see what happens if I change this to an S. Let's see if we get 1. So it is just a sample. So here's our standard deviation. Because I guess we don't have every cook thing in the world, right? So it makes sense. There's our 0 and 1. Beautiful. This is the z-scores for Hershey's. And these are our statistics. We can call them parameters because honestly, they're from a sample. So even though these are the symbols for parameters, we're doing statistics. So what are they here in ones? What are the units of the corresponding z-scores? So what are the units? This was in, I believe the units here are just percentages per z-scores, but I don't know. When I finally hit one I'm not sure about, guess what? I'm going to look at the back of the book. 6-2. They say they are without measurement. Sweet. I was right. Cool. So we got the first ones. Let's get into it. So obviously, did you need to do that? No, but I kind of really wanted to show you that all of this stuff comes from somewhere. So for A, we know that the mean was 0.0004, right? So for A, we know the mean is 0.04, but in our case, we know that's going to be 0. And our standard deviation was 0.997, which we know is approximately 1, and B, no measurement. Because it's just a standardized thing based on percentages. All right, that was 1. Let's go to 2. 1, 2, 5, 8. Here's 2. Based on the data set, weights of chocolates for the bell-shaped graph of normal, what is the area under the curve? Should be 100%, everything. So if we draw this bell-shaped curve, what is the area under the curve? 100% or 1. What is the value of the median? The median is the middle number, right? What is the mode? What is the variance? They give us this mean and they give us the standard deviation. The bell-shaped curve of the normal distribution, what is the area under the curve? What is the value of the median, the mode, and the variance? I'm pretty sure to me, this is different, right? So the area is 100% or 1. Okay, but what is the median, the mode, and the variance? We can, if they're talking about the normal one's going to be, the median's going to be 1. The mode is going to be 1. And the variance is going to be, sorry, the median's going to be 0. The mode is going to be 0. And the variance is, what is the square root of 1? It's still, sorry. What is, so if our standard deviation is 1, the variance is this squared, right? Because the variance is equal to the standard deviation squared. So 1 squared is 1. Now, they don't specify, right? They are not specifying here where these are. So I'm just going to need you the normal data, right? I'm going to do the normal data. So here we go. I have the data. I might as well use it. So when they say that so this was our Z's, right? If we want the median of this, I can do equal, I'll do it for both. So this is for the normal. We know it's going to be H2 to H76. Nice. It should have been 0, but it's close. This was the median. Let's get the mode. Let's get the variance here. All right, so the variance is just going to be this squared. So we already have it. Times itself. Still 1. And the mode from H2 to H76. It's spilled. It's that many. Okay, okay. There's a lot of modes. So I have to take this guy. These are our modes. Our variance is going to be equal to this one times itself, which should be around here. So these are the values for these pieces. I'm going to use it for the statistics. For the z-scores. Can you do this again for the original scores? Sure. You could always do this for the original scores as well. These are all the modes. Now, if they wanted the original, right? The original data, we can just do what? Look, insert. Oops, nope. That's not what I wanted. You can click here, left click it, and then I want to just do. Oh, because I already have this copied. Okay, so I just want this. Not letting me just push one to the right. That's okay. I would normally want this column to be next to this, you know? I don't know why I can't even see the top. Go to view. I don't know how I lost my first one. No. I don't want to save it. I lost the first line somehow. I think I'm for some reason it's hiding it. Let's freeze the top row. I don't know how I lost the first one. So I would just basically use this column and I would do mean median mode for these. I don't really know what happened to it, so it happens. So I would just do it again for the other ones. If they wanted the normal ones, this is what I got. The average is still 0. There's the deviation, there's my median, there's my mode, there's my variance. All right. What's next? The next is 5 through 8. Let's go to 5. IQ scores are 5 through 8. Find the area of the shaded region in the graphs of the adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. The IQ test, which usually happens, so we have 118. We want to know what this is, right? We have to change this to a z-score. So the first thing we have to do is z equals x minus the mean over our standard deviation. Notice this is probably just about everything, right? We know it's going to be like 75% or something, right? So we have 118 minus 100 divided by 15. That's the first step. So our z-score is 1.2. We know that already. So all we have to do is go backwards with 1.2 and we're going to get the percentage. So equals normal dot inverse. Sorry, I think it's norm dot inverse. Yes, it is. All right, so we have our, we don't have our, oh no, sorry. We just have to go the regular way. It just equals normal dot distribution. And we know our z-score is what? 1.2. Our mean is 0. We have 1. And I'm writing sure. We could use the other one, right? We usually use StatCrunch for this, but that's fine. I said it was around 75. It is 88%. We want to use StatCrunch you can see standard went the other way for 1.2, 88.885 or 88.5%. There's 5. 6, 7, and 8. Here's 6. Or now we want to have the other side. So this is going to be 6. So our z-score is going to be 91 minus 100 over 15. Negative 0.6. And notice we want the other way. I would always use just Excel or the table and subtract. But because we have a fancy StatCrunch, we can just flip this. This is the only one that lets you flip it like this. 72.6%, 0.726. Or it's approximately 72.6% of IQs greater than 91. That's what that means. All right, so 7 is the between, so we have to get 2 z-scores. So this is going to be 79 minus 100 divided by 15, and 133 minus 100 divided by 15. So this is going to be negative 21 over 15, and this is going to be 33 over 15. So our low one's 1.4, and our high one is, sorry, negative 1.4, and our high one is 2.2. Should be almost everything. Yep, 90.5 or 0.905. You want the percentage, right? That's what it is approximately. I'll let you do 8 yourself. Let's see if there's anything more challenging. 12, 15, and 21. I'll do 3 more. Let's see what 12, 15, and 21 have for us. 12 is the same thing. Okay, we get to work backwards. Nice. So here's 12, 0.9099. This is giving us the percentage, but we have to work backwards. We can work backwards to get the z-score, right? What do they want? What do we have to do with it? Doesn't say what to do. Okay, so let's just get the z-score for 12. I'm assuming they want to know not the z-score. What is they want to know x. So what IQ score is 9.9099. That's what they want to know. What IQ score is 0.909. So the first thing we can do is work backwards from here. So equals normal dot inverse 0.9099, comma. Oh, we have the mean and the standard deviation, so I think we could be able to just do it using this. The mean is 100, and the standard deviation is 15. I'll try it a couple ways. This says it's an IQ of 120.102. That's what this is telling us. See if that works. If I go backwards, and let's see if I get the 90 percentile. So ready? 120.12 minus 100 divided by 15. Let's just see if we can go backwards. Because the good thing about math is you can go either way you want. So we know it's 20.12 divided by 15. So I have 1.34133. 1.34133. Now let's see if that's exactly right. One point three four one three three. 0.9100. And what did we want? 0.91. Yeah, that's it. Cool. So we got it. So I guess Excel was just great. Can you use backwards using the table? Sure. Okay, so we did 15, 21, 26, and 31. Okay, so 15. I'll do 21 and 26. So let's see what 15 has in store for us. Okay, we have mean, standard deviation, and its normal distribution. Find the probability that a female has a pulse rate greater than 80 beats per minute. 80 beats per minute. So we need the z-score, right? So the first thing I'm going to do is grab my z-score, which is going to be x minus the mean over the standard deviation. Our x is 80. Our mean is 74. The standard deviation is what? 12.5. They have a higher mean and a bigger range or a bigger variation. So it's 6 divided by 12.5. Which is 0.48. So that's my z-score is 0.48. So all I have to do is, and we want it to be greater than 80. So we can use this kind of cheaty one at 0.48. And you will see it is, what is the probability? Has a pulse rate greater? What's her probability? Well, her probability can be seen as a percentage. In our case, it's going to be at 31.6%. That's the probability that that's happening. All right, let's look at 21. For males, find P of 90, which is the pulse rate of separating the bottom 90% from the top 90%. Okay. So we got to go backwards here. And I'm just going to use Excel because we have all the numbers, right? And we want males. So I'm going to do equals normal dot inverse. And we know it's 90. And we have a mean of 69.6. And we have a standard deviation of 11.3. So what is that value? Forgot my decimal point. What a shocker. I'm human. I make a mistake too. So what is that? What is that value? What is that? It's going to be 84.1. 84.1 is the 90th percentile. 84.1. And 26. If the Air Force heights changed to exclude only the tallest and the shortest of men, what are the new height requirements? Okay, so you have to use the body data. Okay, men's heights are, this will be the last one I do. So the mean is 63.7. Our standard deviation is 2.9. Oh, sorry. That was women. I'm pretty sure they wanted men. So the men is 68.6. The standard deviation of 2.8. Find the all right, so the Air Force required pilots to have heights of 64 and 77. So find the percentage of median. So this is the between. So we need the two z-scores. So we need the z for the lower and a z for the upper. So they want the men. So the first thing I'm going to do is get that z-score. So it's going to be the lower one is going to be 64 minus 68.6 over 2.8. And the upper is going to be 64. The upper is going to be 77 minus 68.6 divided by 2.8. Now these two z-scores are going to give me the range to show me the percentages of guys meeting this. So let's get the first z-score. 64.0, I guess, minus 68.6 divided by 2.8. Good, it's lower. It should be negative. That's how I know this is right. So the small one is negative 1.643. Now here's the upper. 77 minus 68.6. It's 8.4 divided by 2.8 is straight up 3. Okay, so let's figure this out. I'm going to go to StatCrunch. And my two values. Or what are my two values? I know the top one is 3. I should be between. This is going to be a negative 1.643. So for this Air Force job, they take 94.948% or what? 94.8% of guys. Beautiful. Let's keep it going. Let's see what else we got. So if the height requirements, oh, sorry, this is Disney World. If the height requirements are changed to exclude only the tallest and the shortest men, what are the new height requirements? Okay, so now we have to go backwards. Now, if we can figure this out, right, we just have to take it away from what? The average, right? We have our average, which is what? The men is 68.6. So whatever value we get, notice in 60, whatever value we get from the positive side, we could just subtract it for the lower side. I'll try to explain what I mean by that. So we're going the opposite way, right? So we're talking guys, and definitely do some more of these if it's not making sense to you. So if I want to go backwards, Normal dot inverse, okay, this is only gonna give me half of this. So we know that we want the exclude the top 2.5%. So what does this mean? So I don't know why I have two calculators. All right, so 1 minus 0.025. 975. Okay, so this is what we're looking at, 0.975. 0.975. We already have the other values, right? We already have the other values of this. What are the other values? The other values are we have a mean of 68.6 and a standard deviation of 2.8. So this means the height requirements, right? The new height requirements is you have to be between, well, I did the small one, right? I just have to do the other one, so it's basically the same thing. But now it's going to be 0.025. Those are the two ranges. So it's going to be between 63.1 and 74.1. So if we just want to exclude these, we know that the smallest guys, you got to be taller than 63.1. You got to be shorter than 74. See, it's different. It changed. So if they changed it to just exclude the 2.5 in this, you can't be super tall. Isn't that interesting? So to be 2.5% on either end, it's going to be between 63.1 and 74.1. So we're going to be between 63.1 and 74.1. These would be the new requirements for heights. All right, so try your best on these. I know these are a little tricky, but at least they're real world situations, so hopefully they're better. This is the last I'm doing today. These two took forever, but good luck and let me know if you have questions.